Problem number 1. How many 4-digit positive integers have at least one digit that is a 2 or a 4? Okay? At least one digit. Okay? It has to be a 2 or a 4. Doesn't really matter how many 2s or 4s or what the other numbers are, as long as at least one of them is a 2 or a 4. So that's a lot of different cases to look at. But the key to this problem is something called complementary counting. Complementary counting. Okay? And complementary counting, looks like I forgot something here, is just counting the complement. And in here, you notice that I spelled complement with an E. And I did that on purpose because this is a different form of complement than a compliment like, boy, your hair sure looks nice today, or you did a really nice job on that picture that you painted, or whatever. That sort of compliment is spelled with an I. See, that's supposed to be an L. Compliment. That's some sort of praise. This is the complement in this case is the thing that completes. Okay, so we have 4-digit positive integers, right? So and we're looking for how many of them have at least one digit that's a 2 or a 4. And the complement of that are the ones that don't have any 2s or 4s in them. Okay? Because if we took all of the numbers that have at least 1, 2, or 4, that sounded kind of strange, at least one digit that's a 2 or a 4, and we also took the number of digits that have no 2s or 4s in them, we would get the total number of 4-digit positive integers. Okay, so how many 4-digit positive integers are there? There's, starting with 1,000, that's the first one. And then we have 1,001, 1,002, 1,003, 1,004, all the way up to the biggest one, which would be 9999. Anything bigger than that becomes a 5-digit positive integer. Okay, so how many numbers are there between 1,000 and 9,999? Well, if we subtract 999 from every number in this list, we will get a set of counting numbers, 1, 2, 3, and so on, all the way up to 999, all the way up to 9,000. So if we counted all of the 4-digit positive integers, there are 9,000 of them. But that's not what we want. That's the whole set. Okay, the 9,000 is the whole set of all the 4-digit positive integers. We're just looking for those that contain a 2 or a 4. That's hard to count. You could probably do it with a lot of casework, but it's easier to count all of the numbers that do not have a 2 or a 4 in it. Okay, so if we look at a 4-digit number, okay, now we can use the digits 1, 3, not 4, 5, 6, 7, 8, or 9, okay, for the first digit. We've also got 0, but the first digit can't be 0, otherwise it would be a 3-digit number, okay? So essentially we have what? We have 7 choices. 1, 2, 3, 4, 5, 6, 7, 8. We have 7 choices, 1, 3, 5, 6, 7, 8, 9, for the first digit. So we have 7 choices for the first digit. And then for the rest of the digits, we could include 0 in those. So we actually have 8 choices for the rest of the digits. Okay, and we could actually draw a tree. The first digit could be anything 1, 3, 5, 6, and so on, all the way to 9. And then we could use 0 through 9, leaving out 2 and 4. We could draw a tree to show how why we multiply. But the result of that is, we have 7 choices for the first digit and 8 for each of the other digits. So if we multiply those all together, what is that? 64 times 56, right? So that's 24, 36, 38, 0, 20, 32, right? And if I add that together, I get 4, 8, 5, 3, okay, 3,584. And that is the number of 4-digit positive integers that do not have a 2 or a 4 in them, okay? So our complement in this case was, let me write that out, I never did write that, did I? The complement, we'll erase that because that's not the kind of complement we're interested in. The complement is the number of 4-digit positive integers, I'm abbreviating quite a bit here, that do not have a 2 or 4, okay? That's the complement that we're looking for, and that's this number here, okay? So if we know we have a total set of 9,000, and 3,584 of them do not have a 2 or a 4 in them, then we know that the rest of these 9,000 have to have a 2 or a 4, okay? So we can just take 9,000 and subtract 3,584 from it. And what will we get? So this becomes a 10, this becomes a 9, this becomes a 9, this becomes an 8, right? So that gives us, 5,416, our final answer, all right? And we use complementary counting. So by counting what we don't want and subtracting it from the whole set, we can get what we do want, all right? So our answer is 5,416.